Good morning, everyone. We are Group 8 and we are going to discuss horizontal curves and its types with corresponding sample problems. First, let's define what a curve is. So a curve is nothing but an arc which connects two straight lines which are separated by some angle called deflection angle. This situation occurs where the alignment of a roadway or railway changes its direction because of unavoidable objects or conditions. The object may be a hill or a lake or a temple or etc. So for the ease of movement of vehicles at this point, a curve is provided. Now curves are usually employed in lines of communication in order that the change of direction at the intersection of the straight line shall be gradual. Now curves provided in the horizontal plane to have the gradual change in direction are known as horizontal curves, whereas those provided in the vertical plane to obtain the gradual change in grade are known as vertical curves. So curves are laid out on the ground along the center line of the work. They may be circular or parabolic. So you might ask, what is the significance of providing curves? So curves are needed on highways, railways, and canals in order to bring about a gradual change of direction of motion, to bring about gradual change in grade and for good visibility, to alert the driver so that they may not fall asleep, to lay out canal alignment, and lastly, to control erosion of canal banks by the thrust of flowing water in a canal. Now at this point, let's focus more on the horizontal curves. So, a highway changes horizontal direction, turning to change the vehicle direction at the point of intersection between the two straight lines is not feasible. The change in direction would be too abrupt and too risky for the safety of modern high-speed vehicles, the driver, and its passenger. It is therefore necessary to interpose a curve between the straight lines. Now, horizontal curves occur at locations where two roads intersect, providing gradual separation between the two. The straight lines of a road are called tangents because the lines are tangent to the curves used to change direction. This curve allows for smooth vehicle operations at the speeds for which the highway was designed. Now, there are four types of horizontal curves, namely simple curves, compound curves, reverse curves, and lastly, spiral curves. So allow me to pass the floor to the next reporter for an in-depth presentation about the simple curve.
Good morning, everyone. I am Zelwit Civilias, and I will be presenting the type of horizontal curve, which is a simple curve. So, a simple curve is an arc of a circle. It is a normal horizontal curve which connects two straight lines with constant radius. The sharpness of a simple curve is also determined by its radius r. So, a large radius are flat, whereas small radius are sharp. It has a radius of the same magnitude all throughout. So simple curves are the most commonly used curves and are usually used to prevent or avoid private properties. So this type of curve is also used to avoid terrains or obstructions that might cause highway construction problems. So in our simple curve, we have several elements that we need to compute prior to the actual layout of our curve. So before we go to the field and lay out our simple curve, we need to compute and determine the values of these elements. So we have PC, which is the point of curvature. It is the point where the curve leaves the first tangent. It is also the beginning of the curve. We have PT, which is point of tangency. It is where the curve meets the second tangent, or the end of the curve. We have PI, which is the point of intersection. It is the point where the two tangents meet. It is also called the vertex. We have tangent distance, which is the distance from the vertex to the PC or the PT. This tangent here is called the back tangent, and this tangent here is called the forward tangent. Next, we have the E, which is external distance. So it is the distance from the vertex to the midspan of the curve, which is measured toward the center. Next, we have the middle ordinate, or m. It is the distance from the middle of the chord to the middle of the curve. We have r, which is the radius. It is the radius of the curve from the center. We have the angle of intersection, or I. It is the angle of deflection between the tangents. It is also called the central angle. We have LC, or the long chord. It is the distance along the curved center line from PC to PT. We have D, which is degree of the curve, which will be introduced later. And we have L, which is the length of the curve, of the simple curve. Next, we will be deriving basic formulas of a simple curve. So we can derive the formulas used in a simple curve by using trigonometric concepts. So the first thing that we can compute is the tangent. So take note that there is a right triangle formed here in this area, so in which the angle formed by the back tangent and the radius is 90 degrees. So the length from the PI to the center of the circle is equal to E plus the radius. The angle at this point is 1/2 to the central angle, which is I over 2, or the 1/2 of the angle of the intersection. So we can now compute the tangent by using the trigonometric identity of tan, or we will just remember SOHCAHTOA, and tan theta is equal to opposite over adjacent. So in this case, the tangent of our angle here is tan I over 2, which is equal to the opposite, which is t, and adjacent radius r. So therefore, we can just transpose this formula. We gain this equation: t equals r tan I over 2. So that is our first formula. Then we can compute for the next element, which is m, or the middle ordinate. So we can extract this triangle in which this angle is 90 degrees, since it is always perpendicular to the chord of our simple curve. So the angle here is still I over 2. Then we have the radius and the half of our long chord, which is LC over 2, because since this is the long chord, then its half would be LC over 2. Now the length of the side would be radius, this radius, minus m, which is the middle ordinate. So we can use the trigonometric identity of cosine, which is cosine theta is equal to adjacent over the hypotenuse. So we have cosine, and our theta here would be I over 2, which is equal to its adjacent, r minus m, and its over the hypotenuse of r. So we can just simplify the following equation, and then we can factor out r and get the formula of the middle ordinate, which is m equals r parentheses 1 minus cosine I over 2 close parentheses. So with this, we can get the formula for our E, which is the external distance. So we can just use the triangle from the previous example. So using the trigonometric identity of cosine, we get cosine I over 2 equal to the adjacent, which is r, over the hypotenuse, which is the radius, plus the external distance, so r plus e. Then we can just distribute cosine I over 2 inside the parentheses. Then we can transfer r cos I over 2 to the right in order to group common terms. Then we can simplify by dividing 1 over cos I over 2 from both sides. Then cosine I over 2 here will cancel, and also from this side it will cancel. So we get E equals to R over cosine I over 2 minus R. We can just factor out R, and remember that 1 over cosine theta is equal to secant theta. So therefore we can say that the external distance is equal to R, close parenthesis, secant I over 2 minus 1, close parenthesis. So our next goal here is to compute the formula of our long chord, or LC, which is the distance from PC to PT. So we can just extract this triangle again, and the labels are still the same. So the goal is to compute for LC, and we can just use the trigonometric identity of sine theta equal to opposite over hypotenuse. So theta here is still I over 2. So sine I over 2 equal to the opposite, which is LC over 2. Since this is the LC long chord, and the half of it would be LC over 2. And its hypotenuse, which is the radius R. So we can just cross multiply and end up with LC over 2 equal to R sine I over 2. If we simplify furthermore, so we get the formula of the total chord length, which is LC equal to 2R sine I over 2. So next we can compute the L, or the length of the curve. So knowing basic geometry, we know that the length of the circle's arc is S equals R theta. Example shown is this example shown is from a sector of a circle in which the arc is labeled S with radius R and angle theta. So we'll be applying this formula to compute for the L, or the length of the curve. So in this case, S would be our L, and with the radius R, and theta would be the central angle I. So take note that I here is in degrees, so we need to convert it to radian. So we need to multiply I here with pi rad over 180 degrees. So we can cancel out the degrees, and so that the remaining angle will be in terms of radian. So therefore the length of the curve will be equal to L pi Ri over 180. So let's proceed on how to get the degree of the curvature, or D. So these elements measures the curve sharpness. So what's the purpose of D? D here is our deflection angle. So we have two different methods in computing for the degree of curvature. First, we have the degree of arc basis, and next is the chord basis. So the purpose of the degree of curvature is to locate the points along the curve. In layouting a simple curve, we usually use PC as the initial position of our instrument. So in locating the points, we position our telescope and line of sight parallel to the tangent line. Once we find the PI, or the vertex, we set our horizontal angle here as 0, and then we deflect. Then the deflection angle formed is where our point is located. So the red points here are our stations, and in DPWH, the distance between station to station is 20 meters in a simple curve. So since D is a measure of the curve's sharpness, a large radius would give a small degree of curvature, which means it has a flatter curve. So the lesser the radius, the sharper the curve. In designing a curve, we need to make sure that our curve is as smooth as possible. So a sharper curve would cause road accidents, and that would give us a higher centrifugal force. So as engineers, we need to make sure that our degree of curvature, or D, is as small or lesser as possible to ensure a smooth curve. So again, we have two different approaches in computing for the D. First, we have the arc basis. So with this, we have a value of the radius in every degree of curvature in a fixed length of arc, which is equal to 1 station. So 1 station is equal to 20 meters. So let's solve for the D in terms of radius. Since this is a sector of a circle, we can just use the formula S equal to R theta, where theta shall be in radian. And since D is in degree measure, we need to multiply it to pi rad over 180 degrees. So 1 station is equal to 20 meters, equal to R, and our theta is d pi over 180 degrees. So we can cancel out the degrees, and we are left with radian. So we can just simplify the equation and get the result of d equal to 1145.916 over r. And to get the radius, we can just cross multiply. So r is also equal to 1145.916 over d. So in the chord basis, instead of an arc, we use a chord of 20 meters. So we can just divide this triangle into two right triangles. So 20 divided by 2 would be 10 on the other side, and 10 on the other side. So with this, we can use the property of sine theta, which is equal to opposite over hypotenuse. So our theta here would be d over 2, and the opposite would be 10 over the hypotenuse, which is r. We can just transpose the following and get a final equation of d equal to 2 arc sine 10 over r. To proceed, in order to apply the formulas that we had just learned, here is a sample problem. So find the length of the curve if the degree of the curve is 5 degrees and the central angle is 72 degrees and 30 minutes. Solve also the radius, tangent distance, external distance, and the middle ordinate. Used arc basis. As we can notice, our basic formulas all involve the radius, so we need to find the radius first. We can find the radius by using the formula for the degree of curve, or D, since it is already given in the problem. We can use this formula right here. D is equal to 1145.916 over R. So you can just cross multiply and get the formula of R equal to 1145.916 over D. We can just substitute directly. D is 5 degrees. We will input this in our calculator and get the value of 229.183 meters. Next, we can find the length of curve by using the formula L equal to pi times the radius times the intersection angle over 180. You can just solve this through direct substitution since we already have our radius, and that would be 290 meters. Next is the tangent distance. So from the formula above, you can already solve this. So tangent equal to the radius, which is this one, and then tan 72 degrees 30 minutes over 2, and that would be 168.044 meters. Next is the external distance. So using the formula again above, we have the external distance equal to r, open parenthesis, secant I over 2 minus 1, close parenthesis. So you can just substitute directly and get the value of 55.006 meters. Lastly, we can find the middle ordinate. So the formula is already here, and we will just substitute the values directly and get the answer of 44.360 meters. And that's all for the simple curve.
Good morning, everyone. I am Maria Aishel V. Hiboni, and at this juncture, I'll be discussing about the second type of horizontal curve, which is the horizontal compound curve. So this is the outline of what I'll be discussing for today. So we will define a compound curve and what makes it different from other types of curves. We will also be tackling about the important elements of the compound curves and where in the field do we actually use a compound curve, and also a sample problem will be given. So by definition, a compound curve is a curve that is composed of two or more consecutive simple curves having different radius but whose centers lie at the same side of the curve and must have a common tangent at their meeting point. So in simple words, basically it is just a curve that is composed of two or more simple curves. So where can we use the compound curve? So we can use the compound curve in expressways if we have to have an exit or entrance in a freeway. Also, the purpose of a compound curve is when we need to avoid something, especially among private areas or subdivisions, from them being affected by the construction. So generally, those are the uses of a compound curve. So an example of a compound curve is this picture. So this is an example of a freeway exit. So again, this is a combination of two simple curves, just like this one here. So what you can see, this is the first simple curve and this is the second simple curve. Moving on, these are the elements that we need in order to compute and design a compound curve. So basically, it just have the same elements as the simple curve. Basically, this is an example of the compound curve. So as what you can see here, we have a two simple curve. Let's just say this red arc here is our curve. So let's just say this is our first simple curve and this one is our second simple curve. So this one is two simple curves, and each curve of course has its respective length of the tangent distance, the vertex, the length of the curve, the length of the chord, the degree of the curve, and the central angle of the curve. As you can observe, there is like this T1, T2, so that is the respective elements of each curve, since as mentioned, it is composed of two curves. So here, this is T1 and T2. This is the vertex V1, V2. This is the point of curvature and this is the point of tangency. So the line that connects the PC and PP is the length of the curve. So this is L1 and L2. The length of the long chord, so L1, L2. And this is the PCC, which stands for point of the compound curve. And this, we have the radius 1, radius 2. This is the degree of the curve 1, degree of the curve 2. And it has its point of intersection, which is here. So if we extend this tangent line here, the back tangent line and the forward tangent line, it forms a point of intersection in this part. So this angle, this is the I1, I2. Take note that the angle here and here is the same over this angle here as well. Alright, so to better understand these elements of the horizontal curve, I will be presenting the sample problem. So let's say that the compound curve has these following elements. The I1 is equal to 25 degrees. The I2, the central angle of the second curve, is equal to 40 degrees. The degree of the first simple curve is 3.5 degrees, and the degree of the second simple curve is 6 degrees. So if the vertex is at station 3470.5, what is the station at PT? So in the problem, we're looking for the station at PT. So in order, we cannot directly solve PT since kulang. So basically, we have to solve for the following elements before we can solve the point of tangent C. So first, we still have to solve for the point of curvature. Since it is not given a problem, we have to solve for point of curvature. And for us to solve the point of curvature, it is you just have to subtract the station of vertex into this line. And to get this line, we have to solve it individually so that we can get the point of the curvature. And after that, we cannot solve the point of curvature PT just by having the value of point of curvature. So we still have to find the L1 and L2 that connects the PC to PT. So that's when we can solve for the station of point of tangent C. So the first step in this problem talaga is to solve for the radius of R1 and R2. Radius 1 and radius 2. Why do we have to solve for R1 and R2? We have to solve R1 and R2 since in the problem we have to solve for L1 and L2. And we cannot solve L1 and L2 without the value of radius. So first step in this problem is to solve for R1. So from the formula that was been derived in the simple curve as discussed by Ms. Lillowet, we all know that in order for us to get is equal to 20 times 180 degrees over pi times the degree. So to simplify that, R is equal to 1145.916 over D. So since given in the problem, we have the degree of the first curve and the second curve. All we have to do is just substitute it in the formula for the radius. Then we can get the value. For R1, we have 327.405 meters. And for R2, we have 190.986 meters. The next step we have to do is to solve for the length of the tangent distance of the first and the second curve. So for us to solve T1, it has a formula of R1, a radius times tangent times the central angle over 2. So for T1, you just have to substitute the value of radius 1 and the central angle of the first curve. So yeah, you just have to do a simple math and then you can get the value for T1 of 72.584 meters and for T2 is 69.513 meters. Now we already have the value for T1. The next step we can do is to solve for A1. So this line naman, since we already have T1, now we will solve for A, this line here. Since it's a triangle, we can use the sine law. Using the sine law, we have a formula of A over sine theta is equal to T over sine beta. For sine beta, we can solve it by 180 degrees minus the given degrees of the problem, which is 40 minus 25 degrees. So if we subtract that with 180 degrees, we can get the value of beta of 116 degrees. So for the theta, we just have to place in 40 degrees and we can now get the value of A of 100.781 meters. Now that we already have the value for A and T1, we can now solve for station of the point of curvature. So given the vertex of station, the station of the vertex minus A minus T1, so just have to substitute those values and we can get a value of 3,297.135. So that is the station of PC. Now we are closer in getting the point of tangent C. Step for this problem is to solve for L1 and L2. So in solving L1, we already have a formula taken from the simple curve discussion. So we all know that in getting L, we just have to use the central angle times the radius times pi over 180 degrees. So for L1, you just have to substitute the given for the central angle for the first curve and the R1, which we have computed already a while ago. So just substitute those values and we can get the value for L1 of 142.857 meters, and for L2 we can get the value of 133.33 meters. Now that we have the value of L1, L2, and the station of PC, we can finally solve for the station of PP. So just have to add everything. 3,257.135 plus 142.857 plus 133.33, and that equates to 3,533.325. So that is your value for the station of PP. So that is everything about horizontal compound curves. I'll give the floor to the next reporter. Thank you.
Hello everyone, my name is JV, and now let's talk about the horizontal reverse curve, its definition, the elements of a reverse curve, and a sample problem. So first, let's define what a reverse curve is. So a reverse curve is composed of two or more simple curves turning in opposite directions. Their points of intersection lie on opposite ends of a common tangent, and the point of tangency of the first curve is coincident with the point of the curvature of the second. Now this point is called the point of reverse curvature, or PRC. Now reverse curves are useful when laying out such things as pipelines, flumes, and levees. The surveyor may also use them on low-speed roads and railroads. This design is not recommended to be used in high-speed roads or railroads, as this would bring discomfort to motorists because of the instant change in direction at the point of reverse curvature, which also brings some safety problems. Despite this fact, reverse curves are being used with great success on park roads, formal paths, waterway channels, and the like. So here are the elements of the reverse curve. So the elements are common to the other horizontal curves except for the point of reverse curvature. Now let's proceed to the sample problem to better understand reverse curve. For our sample problem, the perpendicular distance between two parallel tangents of the reverse curve is 30 meters. The azimuth of the back tangent is 270 degrees and the common tangent is 300 degrees. If the radius of the first curve is 175 meters, determine the radius of the second curve and the length of the two curves. So first, let's illustrate the problem. So I already have a pre-illustration right here. So the azimuth of the back tangent is 270 degrees. So that means this is our T1. And the azimuth of our common tangent T1 plus T2 is 300 degrees. Which means this is also our T1 and this is our T2, which makes this line our T2 also. So from the problem, our offset or the perpendicular distance is 30 meters. So this one here is our radius, so that's R1. And we have given 175 meters, R1. So we have 175 meters as our first radius, and this blue line is our curve, and that's L1 and L2, which makes this line our R2. So So let's not forget our central angle, I1. So this is I1 and this is I2. So from the illustration, we can see that our I1 and our I2 are opposite angles. And since we have our back tangent 270 degrees and 300 degree common tangent, therefore we can get the I. So I is equal to 300 degrees minus 270 degrees. So I1 is equal to I2, which is equal to 30 degrees. Now since we already have I1, we can get the R2 if we have T2. So from the illustration, we can actually draw out a triangle. As you can see right here, we can draw a triangle. So let's draw that one right here. Okay, so we have 30 meters here, 30 degrees, and our hypotenuse T1 plus T2. Now we can already get T1 since we have R1 given from the problem. So T1 is equal to R1 tangent of I1 over 2. So we have T1 is equal to 175 meters multiplied by the tangent of 30 over 2. So from the calculator, we can get 46.891 meters as our T1. So now let's get T1 plus T2. So we can use the sine 30 degree function since we have 30 meters is opposite to 30 degrees and this T1 plus T2 is hypotenuse to 30 degrees. So sine 30 degree is equal to 30 meters over T1 plus T2. Now by manipulating the formula, we can get T1 plus T2, which is equal to 30 meters over sine 30 degrees. So T1 plus T2 is equal to 60 meters. Now by manipulating the equation, we can get T2 is equal to 60 meters minus T1, and we can get T2 is equal to 60 meters minus 46.891 meters. From the calculator, we can get 13.109 meters. So we have our T2. Now having these values, we can now solve for R2, which is equal to T2 over the tangent of I2 over 2. So R2 is equal to 13.109 meters over tangent of 30 over 2. So from the calculator, we can get 48.923 meters. We have our R2. Now using these values, we can now calculate for L1 and L2. So we know that L over I is equal to 2 pi r over 360 degrees. Simply L over I is equal to pi r over 180 degrees. Therefore, L is equal to I multiplied by pi r over 180 degrees. So L1, to get L1, now to get L1, we have L1 is equal to I1 multiplied by pi r1 over 180 degrees. So L1 is equal to 30 multiplied by pi 175 meters over 180 degrees. So we have L1 is equal to 91.63 meters. Same goes for L2. So we have L2 is equal to I2 multiplied by pi R2 over 180 degrees. So L2 is equal to 30 degrees multiplied by pi 48.923 meters over 180 degrees. So we have L2 is equal to 25.62 meters. So that's it. We have the R2 and the L1 and L2.
My name is Carl Go, and I'll be discussing our last topic for today, which is the horizontal spiral curve. The horizontal spiral curve, also known as the transition curve, is a curve of varying radius used to gradually increase the curvature of a road or railroad. Spiral curves are used primarily to reduce skidding and steering difficulties by gradual transition between straight line and turning motion, and/or to provide a method for adequately superelevating curves. In engineering construction, the surveyor often inserts transition curves between a circular curve and the tangent to that curve. The spiral curve is designed to provide for a gradual superelevation of the outer pavement edge of the road to counteract the centrifugal force of vehicles as they pass. The best spiral curve is one in which the superelevation increases uniformly with the length of the spiral from the TS, or the point where the spiral curve leaves the tangent. The curvature of a spiral must increase uniformly from its beginning to its end. At the beginning, where it leaves the tangent, its curvature is 0. At the end, where it joins the circular curve, it has the same degree of curvature as the circular curve it intercepts. Move on to the elements of spiral curve. TS stands for the point of change from tangent to spiral, SC for the point of change from spiral to curve, CS for the point of change from curve to spiral, and ST for the point of change from spiral to tangent. LT stands for the long tangent and ST stands for the short tangent. R stands for the radius of the simple curve, while TS stands for the spiral tangent distance, TC for the circular curve tangent, and L for the length of spiral from TS to any point along the spiral. LS refers to the length of the spiral, and PI refers to the point of intersection between the two tangents. I is the angle of intersection and IC is the angle of intersection of the simple curve. Next, P is the length of throw. X is the offset distance from the tangent to any point on the spiral. XC is the offset distance from tangent to the SC, which is the point of change from spiral to curve. Y is the distance along tangent to any point on the spiral, while YC is the distance along the tangent from TS to the point at right angle to SC. ES stands for external distance of the simple curve, S for spiral angle from tangent to any point on the spiral, theta S for the spiral angle from tangent to SC, and I refers to the deflection angle from TS to any point on the spiral. IS refers to the deflection angle from TS to SC, D refers to the degree of spiral curve at any point, and DC refers to the degree of simple curve. Next, we move on to the derivation of formulas. The first formula we look for is the spiral angle from the tangent to any point on the spiral in radians. To find this formula, we consider a differential arc length at any point in the spiral. Within this differential arc length, we can find that the radius r on the left and right are equal, even though this is a spiral curve. This is because the differential length is very small and thus creates a negligible difference between the two radii. Following the principles of trigonometry, for the subtended angle in radians, the arc length dl is equal to the product of the radius and the subtended angle. This is how we came up with the formula dl equals r times ds. we simplify it to ds equals dl over r. From the property of a spiral that the radius of the curve is inversely proportional to the length of the spiral, we come up with the formula r over rc equals lc over l. We further simplify this into r equals rc lc over l and substitute this in the last formula. Substituting, we come up with ds equals ldl over rc lc. This can now be integrated on both sides to come up with our final formula, which is s equals l to the power of 2 over 2 rc lc. Following this, we look for the formula for the spiral angle at SC, the point between the spiral and the curve. At SC, the length of the spiral is equal to LC. Thus, we substitute SC equals LC squared over 2RC LC, where we can easily cancel the numerator by one of the denominator. This comes out to the formula of SC equals LC over 2RC. Following this, we can also find that when the length of the arc is the standard 20 meters, we can substitute that RC equals 20 over DC. Substituting this, we come up with the formula of SC equals LC/DC over 40 when the arc is 20 meters. Next, we look to derive the formula for the offset from the tangent at any point in the spiral. On the diagram on the left, we can see the line in blue, which represents the tangent, and the red line, which represents the spiral curve. To find this formula, we need to note that if the length of the spiral shall be subdivided into smaller lengths, such as dl starting from ts up to any particular point in the spiral, then the total offset of the point on the spiral shall be the sum of all components of dl perpendicular to the tangent. Therefore, to find this formula, we need to create several different points on the spiral curve which have smaller and smaller spaces in between them. These spaces create triangles, which we can see in the diagram to the right. If we see the triangle on the right, we can see that it's a right triangle whose dx side can be summed to the value of x, which is the total offset distance from the tangent to any point in the spiral, which is what we are looking for. However, we need to find the angle of the right triangle, but this was already formulated in the past formula by the spiral angle at any point, which is represented by the letter s. Thus, sin s equals dx over dl. Since the angle is very small as it is a derivative, sin s can approximately equal to s. S equals dx over dl and dx equals s dl. Since we already found s in the past formula, this is equal to L squared over 2RCLC. We simply substitute this in the last formula and come up with dx equals L squared over 2RCLC dl. We integrate both sides and come up with a new formula for the offset from the tangent at any point in the spiral, which is x equals L cubed over 6RCLC. To find the offset from the tangent at SC, we simply substitute L equals LC and x equals XC. We can see that we can eliminate the numerator and the denominator to come up with a new formula, which is x equals LC squared over 6RC for the offset from the tangent at SC. Next, we look to derive the formula for the distance along the tangent at any point in the spiral. This is similar to the way we derived the last formula, which is the offset. To derive this formula, we need to note that the length of the spiral shall be subdivided into smaller lengths, such as dl starting from ts up to any particular point in the spiral. Then the distance of the point along the tangent shall be the sum of all components of dl parallel to the tangent, instead of perpendicular like the offset formula. So to get this formula, we get the triangle again, similar to the last one, but instead of finding dx, we look for dy. And to do this, we need to use the slope correction formula, y equals s minus c. This is where the horizontal distance is equal to the inclined distance less the correction due to slope, where the correction due to slope is equal to the square of the vertical distance divided by twice the inclined distance. We thus come up with the formula dy equals dl minus dx squared over 2dl. Next, we can find from the last formula for the offset that dx already equals s dl. We simply substitute this again and come up with dy equals dl minus s squared dl cubed over 2 dl. We eliminate the numerator and the denominator and substitute again the very first formula we found for the spiral angle, which is s equals l squared over 2 LCRC. We integrate all sides and come up with the formula for the distance along the tangent at any point in the spiral, which is y equals l minus l to the power of 5 over 40 LC squared RC squared. Following this, to find the distance along the tangent at SC, we simply substitute L equals LC and Y equals YC. Once substituted, we can see that we can eliminate the numerator and the denominator and come up with the final formula YC equals LC minus LC cubed over 40 RC squared for the distance along the tangent at SC. Next, we look to derive the formula for the deflection angle at any point in the spiral. The deflection angle is represented by the variable I. This variable I is the angle that is formed between the tangent and a straight line that intersects directly with any point in the spiral, which is represented by L. This forms a right triangle, where the opposite is represented by x, which is the offset, and the hypotenuse is represented by L, which is the straight line intersecting the point. Thus, sine I equals x over L. Since the angle is very small, sine I approximately equals I. Therefore, I will equal to x over L. X equals L cubed over 6 LCRC, as we have already seen in the past formula derivation. Thus, I equals L cubed over 6 LCRC over L. This allows us to eliminate the numerator and the denominator, which equals I equals L squared over 6 LCRC only. However, we can further separate L squared over 2 LCRC from 1/3, which is, as we know, equal to the spiral angle in the first formula we derived. Thus, I equals 1/3 times S, or I equals S over 3 as the final formula for the deflection angle at any point in the spiral. Next, we look for the deflection angle at SC. And to do this, we simply substitute S equals SC and I equals IC directly to come up with the formula IC equals SC over 3 for the deflection angle at SC. We move on to the sample problem for spiral curves. In this problem, a spiral 75 meters long connects a tangent with a 6° and 45-minute circular curve. If the stationing of the TS is 5,000 and the gauge on the track on the curve is 1.75 meters, we need to determine A, the spiral angle at the first quarter point, B, the deflection angle at the end point, C, the offset from the tangent at the second quarter point. Thus, we are given LC, or the spiral length of 75 meters, DC with a 6° and 45 minutes, B with 1.75 meters, and RC, which we can get from DC by dividing 1145.916 by DC, or 6° and 45 minutes, to come up with 169.765 meters. To find A, the spiral angle at the first quarter point, we use the first formula we derived, which is S equals L squared over 2 RCLC. L equals 0.25 times 75 meters, or 1/4 of 75 meters, since it is at the first quarter point. This comes out to 18.75 meters. We plug this in the formula with the given already, come up with S equals 18.75 squared over 2 times 169.765 times 75, which comes out to 0° and 48 minutes. For the next number 2, we look for the deflection angle at the endpoint. Since it's asking for the endpoint, we use the point SC and use the formula I equals SC over 3, which was the last formula that we derived. SC in this case equals LC squared over 2RC, or 75 squared over 2 times 168.765. Since the answer to this is in radians, we multiply it by 180 over pi to receive the degree value of 12.656 degrees. We simply divide this by 3 to receive 4.213 degrees as our final answer for I. Lastly, for number 3, we look for the offset from the tangent at the second turning point. To do this, we use the simple offset formula of x equals L cubed over 6 RCLC. In this case, since the question is asking for the second turning point, we use L equals LC over 2 or 37.5 meters. We plug this in the original formula and we get 37.5 cubed over 6 times 169.765 times 75 for the final answer of 0.69 meters for the offset from the tangent at the second turning point. That's all for today. Thank you very much.